much for your kind introduction, Professor Adams. First of all, I would like to thank the organizers for giving me this opportunity to speak to you today. So as you can see, the title of my talk is Symmetry Analysis of a Coupled 2+1 Dimensional Hyperbolic System. But before I come to this, I want to give some preliminaries. So first I will talk on the group classification of differential equations. So in this talk, or in this section of the talk, I will discuss what we mean by symmetry, and then symmetries of differential equations, group classification of differential equations, and then I will consider an example of plane emergent polar equation. So what is a symmetry? So a symmetry is a transformation that leaves an object unchanged or invariant. For example, if we consider an equilateral triangle with vertices labeled as 1, 2, 3, then the rotation through angles 2 pi over 3 and 4 pi over 3 leaves the triangle invariant, as you can see from this figure. Another example is, for example, if we consider the rotation of a circle with radius r through an angle epsilon. We consider 2 points x, y and x bar, y bar on the circumference of a circle. So in terms of the radius and angle theta and theta plus epsilon, we can write x equal to r cos theta, y equal to r sin theta, and similarly x bar is equal to r cos theta plus epsilon, and y bar is equal to r sin of theta plus epsilon. So now we can eliminate theta from these two equations, and we can write x bar and y bar as x bar equal to x cos epsilon minus y sin epsilon, and y bar is equal to y cos epsilon plus x sin epsilon. So we now show that the circle remains invariant under this transformation 1. So in fact we need to show that x bar squared plus y bar squared is equal to r squared if x squared plus y squared is equal to r squared. So if we start with x bar squared plus y bar squared, then we write the value of x bar and y bar here. We square this out, and then we use the formula of cos squared plus sin squared equal to 1, and we end up with x squared plus y squared, which is equal to r squared. So this means that the circle remains invariant under the transformation 1. Now we consider an equation in x and y, and we show that this equation is invariant under this transformation 3. So equation 2 can be written in this form, and now we consider x bar plus 1 over y bar, and this is equal to, we write its values of x bar is this, value of y bar is this, and we simplify and we see that this is equal to x plus 1 over y. So this means that x plus 1 over y is invariant under 3, or in other words, this equation will be invariant under the transformation 3. Now the transformations 1 and 3 are very special and are referred to as Lie transformation groups, or just Lie groups. Now, can differential equations be invariant under Lie groups? we consider a simple first order differential equation, ordinary differential equation, and we consider the Lie group given by 6. So it can be seen easily that dy bar or dx bar is equal to this, and x bar y bar cube is equal to that. Thus from these two equations we see that this is equal to that provided dy by dx is equal to xy cube, which means that the differential equation phi is invariant under the Lie group 6. So as another example, we can show that this first order ODE is invariant under this Lie group. Okay, now we come to symmetries of differential equations. About 200 years after Leibniz and Newton had introduced the concept of the derivative and the integral of a function, solving ODEs have become one of the most important problems in applied mathematics. It was then that Sophus Lie, a Norwegian mathematician, got interested in this problem. He got inspiration from Galois theory for solving algebraic equations that had become widely known around 1850, mainly due to the efforts of Lewis. So Lie showed that the majority of the known methods of integration of ordinary differential equations, which until then had seemed artificial, could be derived in a unified manner using his theory of continuous transformation groups. So this method is known today as Lie group analysis and is indeed the most powerful tool to find the general solutions of differential equations. In the last 6 decades, there have been considerable developments in Lie group methods for differential equations, as can be seen from number of research papers, books, and new symbolic softwares devoted to the subject. A Lie-point symmetry of a differential equation is an invertible transformation of the dependent and independent variables that leaves the equation unchanged. Determining all the symmetries of a differential equation is a formidable task. However, Sophus Lie realized that if we restrict ourselves to symmetries that depend continuously on a small parameter and that form a group, one can linearize the symmetry condition and end up with an algorithm for calculating continuous symmetries. So now we come to group classification of differential equations. Now many differential equations of physical interest involve parameters, arbitrary elements or functions which need to be determined. Usually these arbitrary parameters are determined experimentally. However, the Lie symmetry approach through the method of group classification has proven to be a versatile tool in specifying the forms of these parameters systematically. The problem of group classification was first carried out by Lie himself in 1881 for a linear second order partial differential equation with 2 independent variables. Later, various people, including Ovzhonikov and Ibrahimov, applied Lie's methods to a wide range of physically important problems. So how does one effect group classification? We begin the procedure by obtaining the principal Lie algebra of operators of the given family of differential equations. This is the Lie algebra admitted by any differential equation in the family. it happens that for particular choices of the arbitrary elements of the family, the equation admits an extension of the principal Lie algebra. So the problem of construction of all different cases when an extension of the principal Lie algebra occurs is called the problem of Lie group classification. An important part of the group classification of a given family of differential equations is the use of equivalence transformations, which are transformations of the independent and dependent variables that leave the family of differential equations invariant. So this allows one to divide the family into disjoint classes. The equations in each class are equivalent to each other. The representative of each class simplifies the determining equations. So as an example, if we look at this second order ordinary differential equation, which has a constant alpha in it, the principal Lie algebra is spanned by the single operator x1. And then we have extension in two cases. When alpha is 1, we get an additional operator x2 given by this, and when alpha is 0, we also get an extension by one operator, in this case delta by delta x. So now I give you an example of group classification of Lane-Emden-Fowler type equations. So I will skip the history of this equation and I will come to the equation which I am going to discuss. So this is, we call a generalized Lane-Emden-Fowler type equation, which is a second order ordinary differential equation. So in this equation we see that we have n and nu as constants, and f is a function of the dependent variable y. So we are going to perform Lie group classification of this ordinary differential equation. So first we look for the equivalence transformations for our equation. So we recall that an equivalence transformation x bar and y bar is a non-degenerate change of variables such that the family of equations A remain invariant. So equivalence transformations are essential for simplifying the determining equation and for obtaining disjoint classes. So what we do is first we write the equation 8 as system of the two equations as given in 9, and then the generator of a one parameter group of equivalence transformations is given by y equal to this. The prolongation of the derivatives gives y tilde, where zeta xx are the usual prolongation formulas, and wx is given by this formula, and dx tilde is given by that. So the determining equations are given by these two. And when we expand these, we see that we get mu x0 and eta x0, and then in place of y double dash we write this, which comes from the equation, and after splitting we get 1, 2, 3, 4 equations to be solved for xi and eta. So solving this overdetermined system of 4 PDEs, we get the values of xi, eta and mu. So we see that there are 3 constants, so we get the 3 operators y1, y2, y3, and hence the one parameter group of equivalence transformations corresponding to each operator is given by this, and their composition can be written as 16. Okay, now we look for the determining equation and the principal Lie algebra. If x given by this expression is an admitted generator of a symmetry group of equation A, then it has to satisfy this, where x2 is the second prolongation of x. So expanding and then replacing y double dash by this its value, and then splitting with respect to powers of y dash gives us an overdetermined system of PDEs. Now from the first two PDEs we get the values of xi and eta in this form, and then we look at the third and fourth equation here. We insert the values of xi and eta in equation 20, we obtain this. Now if we differentiate this equation twice, we get this equation. And since we require that f is not a linear function in y, we are forced to have a equal to 0. So in this case, our xi and eta becomes xi equal to bx and eta equal to cxy plus dx. Now we substitute the values of xi and eta in our fourth equation, which is equation 20, and this gives us this. So invoking the expressions of xi and eta in 21, we get this long equation 24. Now if in this equation we assume that f is an arbitrary function, then all the terms in the parentheses of equation 24, they vanish, and this gives us the value of b, c and d. So c and d are 0, where b is a constant. And then we insert these values of b, c, d in equation 23, and we get b equal to 0. So this means that xi and eta are 0, meaning that our principal Lie algebra of 8 is trivial. So now we derive the classifying relations, and finally we do the group classification. So the function f depends upon y only. Thus equation 24 only holds if its coefficients identically vanish or they are proportional to a function of x. So in this case we have these equations where r, q, p, h and g are constants. Thus equation 24 becomes equation 26, and this is our classifying relation. Now this relation is invariant under the equivalence transformations which we obtain if we have r bar equal to r and so on. Now the relations in 27 are used to find the non-equivalent forms of f, and this leads to the following 8 cases for the function f. So the first case is when f is an arbitrary function, but mu is not equal to 1 minus, n is not equal to 1 minus mu over 2. And in this case, no Lie point symmetry exists. And case 2 is when n is equal to 1 minus mu over 2, and f is an arbitrary function but not in the form obtained in cases 4, 5 and 6. We do get one Lie point symmetry x given by 28. The third case is when f is linear. Now this case is not so interesting because it is well known and the corresponding equation has SL3R symmetry algebra. The case 4 is when we have the value of f to be a constant minus delta y square over 2, where delta is equal to plus minus 1 and k is a constant. In fact, this case 4 has 6 subcases. So the first subcase is when the value of n is equal to 2 nu plus 3 and k is 0. In this case, we have one additional Lie point symmetry. The second case is when n is equal to 12 nu plus 13 and k is 0. Here the corresponding equation admits the same symmetry as case 1. And similarly, we have case 3, 4, 5, 6, depending on the values of n, the relation between n and nu. You can see they are different. Then we go to case 5. In this case, we have a power function, y to the power minus sigma. So this case has 3 subcases also, depending on the values of the relation between n, sigma and mu. So this is case 5.1, 5.2, 5.3. And case 6 is when our function f is an exponential function. And here we also have 3 subcases. So I will not go into details of these cases. And then finally we have case 7 and case 8. Case 7 is when f of y is a log of y, and case 8 is when f is y log y. So we obtained 8 cases for the function f. So for these 8 cases, we can integrate the original equation completely. For example, here we consider 3 cases, and we recall that for any 2-dimensional Lie algebra with symmetries G1 and G2 satisfying the Lie bracket relation G1, G2 equal to lambda G1 for some constant lambda, the usual reduction of order is through the normal subgroup G1. So we start the reduction with G1 if we have such a case. So here we consider case 4.1, and the corresponding equation 8 admits 2 symmetries, in this case x1 and x2, and since the Lie bracket x1, x2 is equal to a constant times x2, so we start the reduction with x2. The invariants of x2 are found from the associated Lagrange equation, and these are given by t and s. So using these these invariants, our equation reduces to the first order equation, which is very simple to integrate. And then reverting back to the variables x and y, we obtain the first order differential equation here, which can be integrated, and hence we have the quadratures for our equation 8 for the given value of the function f. So similarly, I have given the solutions for 2 other cases, which I will skip now. So this was a brief introduction to the Lie group analysis or Lie group classification of the ordinary differential equation. So now I come back to my original talk. So the preamble of the talk is the following. We performed Lie group analysis and Noether symmetry classification of a coupled 2+1 dimensional hyperbolic system, which is given by this. 2 refers to the space variables and 1 refers to the time. we show that the principal Lie algebra, which is 6-dimensional, extends in several cases. And we further show that 3 main cases arise in the Noether classification with respect to a Lagrangian. And moreover, we establish conservation laws in the cases which admit Noether point symmetry. And then finally, we give the concluding remarks. So, a brief introduction to our problem is that in this paper in 1991, the system of equations was investigated and the boundedness and blow-up of solutions were discussed. Also, the uniqueness and global existence of solutions of this system were investigated by the same authors in 1998. Such hyperbolic problems appear in several branches of applied mathematics and can be used to model, for example, chemical reactions, heat transfer, or population dynamics. So, motivated by the work in this paper, the authors of this paper in 2013 studied the existence and blow-up properties of solutions to initial and boundary value problems for nonlinear parabolic and hyperbolic systems with variable exponents. So from here we extended these variable exponents to general functions f and g. So we consider a coupled hyperbolic system in 3 dimensions, namely given by this. These are second order PDEs, where f is an arbitrary function of v and g is an arbitrary function of u. So we note here that we are going to exclude the cases when f and g are linear, because then they are not so interesting to us. So first we look at the Lie group classification. The symmetry group of the coupled 2 plus 1 dimensional hyperbolic system will be generated by the vector field of the form X, where tau, xi1, xi2, eta1, eta2 are functions of the independent variables txy and dependent variables uv. So thus the system 3,4 admits a Lie point symmetry 5 if it has to satisfy these 2 equations 6 and 7. So the expansion of these 2 determining equations 6 and 7 yields an overdetermined system of 66 partial differential equations. These equations, after some tedious manipulation, lead to the following cases, which we present in tables 1 and 2 below. So here alpha, beta, p, q are constants with alpha and beta not equal to 0. So the first case is when f and g are arbitrary functions. In this case we obtain the principal Lie algebra, and in this problem we have 6 operators for principal Lie algebra. The first 3 are translations, and x4, x5 are Lorentz boost, and x6 is the rotation. So we can formulate this in a theorem. Suppose that f and g are arbitrary functions, then the generators x1 to x6 form the principal Lie algebra of the system 3 and 4. So other cases now we consider, the next case is when the function f is a power function v to the p and g is u to the q, provided p and q are not equal to -1. In this case we have one extra symmetry operator given by this, which is again a scaling. The next case is when f is equal to v to the minus 1 and the function g is arbitrary. In this case, we also have one additional operator, which is scaling. The next case is when f is arbitrary but g is equal to u to the power minus 1. So in this case also we get one extra symmetry operator given by this. And if we have both the powers p and q to be minus 1, then we have two extra symmetry operators which are both scaling. And the interesting case is when both the powers of p and q are 5. In this case we have 4 extra symmetry generators. The first one is the scaling and the other 3 are inversion. So this was the Lie group classification. Now we move on to the Noether symmetry classification of the system. We recall that the Euler-Lagrange operators are given by delta where delta u equal to this, delta where delta v equal to that. Now we can see that the coupled hyperbolic system are Euler-Lagrange equations for the first order Lagrangian L given by this. Now we consider a vector field G given by this. A vector field G of this form is called a Noether point symmetry generator corresponding to the Lagrangian 14 if there exist gauge functions B1, B2, B3 such that this equation 16 is satisfied. So now we recall this theorem here. If G as given in 15 is a Noether point symmetry generator corresponding to a Lagrangian L, then the Euler-Lagrange equations possess the associate conserved vector Txy with components given by these expressions. That is dt of t plus dx of x plus dy of y equal to 0 on all solutions of Euler-Lagrange equations. Now, however, we can avoid the complications of determining the gauge functions if we use the general method of multipliers to find the Noether point symmetry generators G. So the pair of functions q, which is given by q1 and q2, is a multiplier yielding a conservation law of the Euler-Lagrange equations of a first order Lagrangian if this equation holds identically. So now we state a theorem which is in 2 parts. The first part is when if G as given in 15 is a Noether point symmetry generator corresponding to a Lagrangian L, if and only if the components of G in evolutionary form are multipliers Q1 equal to this and Q2 equal to that. And the second part is that multipliers as given in 24 are solutions of the determining equations 25. So if we use these theorems, then the expansion of the determining equation 25 in our case for our system yields an overdetermined system of 71 partial differential equations. And these equations lead to the following cases. Case 1 is when f and g, the functions, are arbitrary functions. In this case we obtain 6 multipliers, and each multiplier gives the components of a variational point symmetry, and these are given by the q1 multiplier is given by this, and the variational point symmetry is our rotation x equal to this. So similarly we have the multiplier Q2 given by this Q3, Q4, Q5 and Q6. So corresponding to these 6 multipliers, we have 6 conserved vectors which we can write. So the first one will be T1, X1, Y1 given by these expressions, and this gives us the angular momentum conservation laws. Similarly, the second multiplier gives us this conserved vector, and this is boost momentum conservation law. So these are the expressions for the conserved vectors corresponding to multiplier 3 and 4 and 5 and 6, and the last one is the energy conservation law. So that was case 2. Now case 1. Now coming to case 2, in this case we have power functions. Our function f is equal to v to the power p, and g is equal to u to the power q, but p and q has to satisfy this relation. So in this case we obtain an extra multiplier which is given by q7, and this corresponds to the variational scaling symmetry. The corresponding conserved vector has the components given by this expression, and this gives us the dilational energy conservation law. The case 3 is when our function f is v to the 5 and g is u to the 5. In this case we obtain 4 extra multipliers, and these are given by Q7, Q8, Q9 and Q10. These correspond to variational symmetry, which are scaling, and 3 Lorentz boosts. So corresponding to these multipliers, we can write the conserved vectors as follows: 7, 8, 9 and 10. So concluding remarks. In this talk we have performed a complete Lie group analysis and Lunar symmetry classification of a coupled 2 plus 1 dimensional hyperbolic system. And some of these results were published in this paper. For future work we plan to study exact group invariant solutions and their properties. So I would like to thank Stephen Enko for helpful remarks on this work and assistance with the Maple computation. So we used Maple to do the computations for conservation laws and so on. So these are some references, and thank you for your attention.
Thank you very much, Prof. Any question or comment regarding the call? Yes, please.
Hi, Mr. Career Prof. I think fundamental and very good possible about I have a very good question here. So you, of course, your research is starting from given equation or given system equation and try to determine the stage of the group to determine the class of equation, right, which has a given or which has some symmetry. So my question is the following: if you are given algebra, the algebra, what kind of equation can you at some way determine what kind of equation will admit that given the algebra as symmetry of the algebra of symmetry? Given symmetry of the algebra, then what kind of equation will admit this kind of simple or algebra symmetry?
If you are given the symmetries Or symmetry algebra.
For example, the algebra field given.
Yes.
For example, E2, let's say. So what kind of equation you can keep E2 as a symmetry, as algebra symmetry?
What can you?
There's some research about that, and this is other opposite direction, right? If you have the equation, you can become symmetry. But now given symmetry, given the algebra symmetry, you want to become an equation which eliminates this kind of symmetry.
Yes.
Is there some research about that? Can you?
No, I haven't looked at the problem like this. But we can discuss and look at the problem like that.
Hey, thank you. Again, that's a very nice talk. Just the n equals 5 case seems very interesting to me. It's very, it seems reminiscent to the wave equation where you have translation, you have rotation and hyperbolic, and then you also have the inversion.
Yes.
So are those algebras isomorphic in the 2 plus 1 dimensional wave equation?
I didn't check that, but these are wave equations. They're hyperbolic equations, basically. So.
Yeah. So yeah. So do you have any intuition of the fifth order?
Fifth order.
Yeah. So why the number 5 is coming out, or?
I don't know. Maybe the physicists, people from physics can tell us, but I have no idea why it's so, important.
Yes,
my question is regarding integrability. You have parameters Q and T. Question is for what kind of parameters T and Q such that a system is completely integrable, either in a sense of a pair. Thank you.
Okay. So your question is that for what values of P and Q the system is integrable. So I haven't looked at that problem, of integrability for the system.
Any more questions?
This short question and clear question. Since your differential equation has you have the Lagrangian, but in the Lagrangian you don't have explicit time dependence. Can you explain why the Lagrangian doesn't have explicit time dependence? If I'm not mistaken.
This is the Lagrangian, no? For this system.
Yeah, but I think you write the Lagrangian something of x, y, and u, derivative of ut, us, uy, but no, not explicit in time. I think next slide.
Next slide.
Yeah, that one. So why there is no time dependence explicit?
Oh, I think I missed the variable time.
I see.
I missed it. I should be there. Yeah, that's P has to be there.
Any more? It is a strange, isn't it? Try to solve the ordinary differential equation, going back to the PDE to come back to the solution. Is it the wrong way through? Can you find it more easy way? Shortcut? Okay, thank you very much for interacting for the team. Yeah.